So let's look at it, see, just to make sure everybody's happy with it. Given the following sampling distribution, now that saying it's a sampling distribution is important to us because that means in our, hierarchy, we had that population, and that population has a standard deviation and a mean. Then we had our sample distributions, which are just the samples one takes. And remember, those mimicked our population, right? Whatever our population's like. And they all had their own sample mean and sample standard deviation. But then as long as our sample size was large enough, our sampling distribution, essentially our distribution of samples, sampling distribution, if our sample size was large enough, then this would be normally distributed. And it would have a mean for the sampling distribution of means. So a mean of the means, and that mean of the means was equal to, is equal to the mean of the population, right? And is an average of all these little means. If we average every mean that you could possibly take, we will get the mean of the actual population. And it has its own standard deviation, which we called standard error, or you could say standard deviation of the distribution of means, but standard error is handier. And we know that standard error is related to the original standard deviation, and we can find it by dividing by the square root of our sample size. Now, this rule for standard error is very important that we connect that to a distribution of means. This sampling distribution is specifically a distribution of averages, a distribution of means. We're taking the average of each of these little samples and looking at the population of those little averages. The average of those averages should be our population average. And the standard error for that distribution of means is found by taking the standard deviation of our original population and dividing by the square root of our sample size. That's a little bit of a mouthful, I know. But if we were distributing something else, if we were, instead of looking at these sample means, if we were, say, looking at sample medians, or looking at a distribution of standard deviations themselves, or a distribution of proportions, or a distribution of anything other than means, this formula for standard error would be different. So this formula for standard error is specifically the standard error of a distribution of means. Now, we won't do a lot of other sampling distributions. We will do one other, and that's a sampling distribution for proportions. We'll talk about that in a little bit. And its standard error formula will be different. So this standard error formula is specific to the standard error for means. Okay. So if we look at this sampling distribution has a mean, okay? The mean of our sampling distribution is 55. That tells us that the mean of the original population that this data came from is also 55. And if we look at it, it looks like the standard error here, our standard error, looks like it's equal to what? It's handy. And we know that in a distribution of means, which we're told this is means, we know that the standard error for a distribution of means is equal to our original standard deviation divided by the square root of our sample size. So we know that that 1 has to be equal to the original population's standard deviation divided by the square root of our sample size, which is 36. Fair? So 1 has to be equal to our standard deviation divided by the square root of 36 is 6. It was nice of them to give us a easy square root number. But even if it's not, if it was some weird decimal, it's okay, we could handle that. Multiply both sides by the 6. 6 has to equal our 6. So we can go from any standard deviation of a population to the standard error of the sampling distribution. We can go back and forth between those as long as we know our sample size. If we change the sample size, we change that standard error. The bigger the sample size, the smaller the standard error. That's going to become really important in Chapter 9. The bigger that sample size is, the more accurate all of your individual averages are, so the tighter your sampling distribution is.
Say that again one more time.
The larger the sample size is, the more accurate your samples are, so the tighter the sampling distribution is. Big sample size means tight sampling distribution. Thus, big sample size means small standard error. And of course, one of the reasons I like this question is it gives us a chance to kind of review our kind of ideology for Chapter 8. I don't know if ideology is the right word there, but our ideas there for Chapter 8. Now, see, this other question, population of values has a normal distribution. Okay. Our original population doesn't have to have a normal distribution, but having a normal distribution means our sampling distribution is going to be normal with any sample size. So even with a small n, we know our sampling distribution will be normal. Now, because the sample size in this question is 81, the sampling distribution was going to be normal anyway. Fair? But even if this sample size was really small, even down to n equals 1, we know our sampling distribution would be normal. By the way, if your sampling size is 1, then your sampling distribution looks like your population. It is exactly your population. Just fun fact. So the fact that we're told the population is normal isn't significant in this particular question, isn't necessary in this particular question. But if this question came up on your homework and this sample size is a variable value. So if you had a sample size, say, of 22 in your particular problem, usually a sample size of 22 wouldn't be big enough to make our sampling distribution normal. But we were told our population is normal, so our sampling distribution is normal regardless. Does that make sense? Find the probability that a single random selected value is greater than 83.7. Okay, that is a chapter 7 question. So chapter 7 says, okay, normally distributed data with a mean of 81.4 and a standard deviation of, it's a huge standard deviation, consider it, 67.9. It's massive by comparison. If we want to know the probability that a single random selected value is greater than 83, okay, that's going to be, say that's 83, that's this area. And you remember doing that from chapter 7, right? And that's going to be, gosh, that's going to be somewhere around 50%. Pretty close. So we would do, since it's greater than, we'd want, well, we don't have to do the 1 minus, depending on your, you guys are probably going to be using the calculator. So we could just go normal distribution from 83 to 1 E99 with an 81.4 and a 67.9. Or you could go 1 minus the negative 1 E99 to 83 if you didn't want to have to change that 1 E99 thing. But when you do that, I would expect that to be super close to 50.
Wait, 5490?
0.54? I expect it to be close to 50, but a little bit less.
I got 0.486.
Oh, I did my thing backwards.
Okay. Which if you do 1 minus, then it would work.
Yeah, hold up. Yeah, that's what.
And we know it had to be less than 50% because it's to the upper portion.
Yeah.
Okay. So that's just, you might ask, why are they asking us a chapter 7 question here? But mostly because they want to compare it to our chapter 8 question. We're then asked, find the probability that of a sample size 81, or that a sample of size 81 is randomly selected with a mean that's greater than 83.7. So the difference here is, what's the probability of grabbing a single value of 83 or more versus what's the probability of getting a big sample whose average is 83.7. Now, you know that your average should be close to the population's average, right? So it's still a normally distributed sample. The difference is, because it's an average of 81 values, that distribution is going to be much tighter than the individual values. So because this is a sampling distribution question, we know that because it's we're finding the mean of a sample size of 81. So our population here is a distribution of means as opposed to a distribution of values. We still want to know, okay, what's the probability of being greater than 83? But what's different in the sampling distribution is that this standard deviation is going to be significantly smaller than that 87.9 or 67.9. it's going to be the standard error of our sampling, or standard deviation of our sampling distribution, which we've been calling standard error. So how do we find that standard error? If only we had some nice little formula for it. For a distribution of means, it's our standard deviation of our population divided by the square root of our sample size. So in this case, it's the 67.9 divided by the square root of that strangely convenient 81. So 67.9 divided by 9 is approximately, what, 7-ish?
611.1?
7.5.
Divided by 9, not multiplied by 9.
7.5.
7.5.
Yeah, 7.54.
So that's standard error, 7.5. So much, much tighter. Fair? So while this, this is just how it's coming up in the drawing, but notice in this drawing, there's much more of that big top part of that bell that we're adding in. Here, we're more out into the tail. We're still less than one standard error off of our mean. So it's still pretty close. So the odds should still be, probably 30s or 40s. But it's going to be much smaller than our chapter 7 question.
That's weird.
What's it doing?
Oh, I don't know how I even came up with the right answer for the first one, doing what I did. I'm confused on what I did. I don't know. It's weird.
Did you try to solve it again? Did you put the 67.9 equals sigma divided by the square root of n and try to solve it?
No, I don't know what I did. I don't know. I just need to do this problem some more because it's, yeah.
Well, you have to be a little bit careful, or a lot careful, between these two questions, because in this first one, we're going from the sampling distribution data to the population. We're going that way, right? Because we're given information about the sampling distribution and asked about the population. Here, we're going from what we're told about the population to the sampling distribution. So there's no solving involved. So instead of multiplying, like we did down here, when we multiplied by that 6, we're doing that just straight division. If that helps. But this would still be a normal distribution. It would still be 83 to infinity. It still has a mean of 81.4 because the mean of the sampling distribution is the mean of the population. It just has that smaller standard error. What does that value end up being? I guess it's in the 30s, but it could still be in the 40s.
0.3802.
Or 38.02% if you wanted to. I was going to go 0.3802. Round it off to however many decimals they ask for.
Are you recording this?
Yes.
Where
And
are
we'll
you
do a
putting in
couple
your
of these. What's up, Michelle?
when you're entering normal distribution in your calculator, are you doing the normal CDF? Because I'm getting.
Yes. Always.
Okay.
Always for normal distribution. The normal distribution PDF gives you the specific height of that bar, which is a weird thing that we don't use for anything. So,
Okay. I'm getting a little bit different of an answer unless I answered it wrong. So I'm redoing it.
It could be
Yeah,
because in the note on the screen there you wrote 83, but the actual
oh,
value is 83.7.
Oh, you're right. Good call. Okay. Yeah, because I was getting like 0.415, but that makes sense.
sorry. Thank you, Andrew. It's close enough, right? Oh, it could be 81.4. So that should be, that's 81.4. Oh, no, yeah, that's 0.7. Okay. Sorry. 0.7. Just changed it a little tiny bit, right?
Yeah. Yep, that was it.
Okay. Thank you, Andrew. I always say the easiest way to do math is to have about 10 people behind you who can go, dude, it's a 7. Makes the world so much easier, I tell you. Okay, so we're going to do some more examples of this, because this does take a little bit of getting used to. But like most other things that we've done, the calculations here and what we're actually doing here isn't that complicated if we can keep track of all the junk, all of what we're asked for, all of the language. You know, this is not a mechanically difficult process. It's a conceptually difficult process. You know, these do start to get tough, but not tough because, you know, solving this for stigma was hard. It's tough because keeping track of the sampling distribution and the sample standard deviation versus the population standard deviation versus the sampling distribution, population distribution. That's the hard part of this, and that's what takes some time and some practice. So be okay with yourself and that taking a while to get comfortable, but do, you know, focus on that language and focus on those details. So I want to do another problem like this first one, but I want to make it, this is a subjective opinion, but I want to make it a better problem. One, I want to give it some context. So like a little bit more of you know, have some meaning on what these differences are. And two, how that 67.9, that huge standard deviation for that population, made it a little less dramatic than it could be. So I'm gonna turn this into a higher drama example and see if we can, see if that helps. Before I do that though, any questions on either of these or anything else you wanna ask before we do that? Okay. So it doesn't have to be, you know, too high drama here. There's just some context is good. So, oh, you make, what do you want to make? You make cutting boards. Because it's fun. It is fun. You make cutting boards. If you want to learn how to make cutting boards, let me know. I'll teach you how to make cutting boards. You make cutting boards. Your period. Your average mean board is, oh, I don't know, how about 16 inches long, just kind of small actually, with a standard deviation of, let's make that fairly large, of 8 inches. So I want to stop there for a second. So what we're describing here is a population, the population of cutting boards you make. We know from what we're told here that the average cutting board is 16 inches long, with a standard deviation of 8 inches. Now that standard deviation of 8 inches is still fairly large in comparison to that 16, right? And if somebody asked us if this population was normally distributed, which frankly is not an unreasonable question, it might be a little, at first, tough to kind of decide, well, how am I supposed to know if this original population is normally distributed? But let's look. If it was normally distributed, that would mean all of our cutting boards should be within 3 standard deviations above and 3 standard deviations below, right? So if we go up 3 standard deviations, that's an extra, what, 8, 16, 24. So 16 plus 24 is, what, 40 inches? Which would be a massive cutting board, but okay, there you can make some really big cutting boards and they're kind of fun. But if we go down 3 standard deviations, that's negative 8. Can we make a negative 8-inch cutting board?
No.
I did abstract mathematics. I can't even make a negative. No, you can't. No, it doesn't make any sense. So what does that tell us about our data? It can't be normally distributed because the empirical rule doesn't make sense. And it's frankly probably skewed.
Right.
Right.
Skewed right.
Does that seem reasonable?
Yes.
So, let's get rid of that. So you find a sample of, how many of your cutting boards? Let's say 50 boards. Because you're selling them to a local real estate company because they want to give them as gifts to people who buy their houses. Yes, I'm making 50 cutting boards for a real estate major. Anyway, it's just like, where am I going to come up with these examples, right? You find a sample of 50 boards. What is the probability, if they're randomly selected from your pile of cutting boards, what is the probability that the mean or the average board is longer than, let's say 20 inches? So again, I want to think through this. If we look at our, example distribution of cutting boards here, a board that's 20 inches or longer in our population of cutting boards, well, 20 inches, that's not even 1 standard deviation above the mean. That's a half standard deviation above the mean, right? So how many of our cutting boards here are going to be 20 inches or longer? Well, quite a few of them. Fair? So what's the probability that an individual cutting board is larger than 20 inches? Well, pretty high. But is that what's being asked?
No. It's asking
No.
if it's longer.
It's not asking if it's longer.
It's asking what is the probability that the mean or average board is longer than 20 inches.
So it's not asking if a board, a specific board, is longer than 20 inches.
No.
It's asking if our average of 50 boards
Yeah.
is greater than 20. Fair? So I'm just going to say here, chance that one specific cutting board is longer than 20 inches. You said that was pretty high, right?
Yeah.
So, okay. You said high. You know, probably, 40% or something like that. And frankly, it would depend on how they're distributed. We couldn't even use our normal distribution tool on that to find it because we don't know what the skew is. But again, it's not what this question is asking. This question is asking, what is the chance that the average of 50 boards is bigger than 20 inches? What should, theoretically, what should the average of our 50 boards be? Theoretically, it should be pretty close to 16, right? But theoretically, any randomly selected board should be close to 16. But for an individual randomly selected board, being 20 inches away, well, that's half a standard deviation. That's not a big deal. That's pretty good. For an average of 50 boards to be 4 inches longer than the average of our population, that's much less likely. Much less likely. Because our sample size is 50, we know that our sampling distribution has to be normal, right? It's normal with a mean of 16. And again, here, this 16 is a board length, right? This 16, that 20, this, 24, those are individual board lengths distributed in our population, right? This 16, okay, it's the same number as that one, but this 16 is an average of 50, being 16. All the values in the sampling distribution are not lengths of boards anymore. They are averages of 50 boards.
Which makes it automatically a normal distribution every time.
As long as our sample size is above 30, yes.
Right.
Forces it to be normal.
Above 30 forces it to be normal.
For means, yes.
For means.
Yep. And the standard deviation there, we might expect it to be, the same as this 8, but we know it's not. We know it's tighter, right? Because our individual boards are all spread out, but our averages of 50 are much tighter. So how do we find that standard error?
With the equation.
with the equation for standard error for means.
For me.
So that's going to be that 8 divided by the square root of our sample size, 20. Finally get a sample size that's not a perfect square today. 20. Why did I say 20? You guys are looking at me like I'm crazy. What should it be?
50?
The 50.
Okay. I get
I told
scared.
you, it's great to have 10 people behind you going, no.
To hear Andrew saying, that's not correct, sir.
Like you guys would call me sir.
It's me.
I don't know why I reduced that. We're going to have to find its decimal anyway, but force of habit. So what is that? 1 point something, right?
1.13.
1.13. Thank you. So that 1.13, so if we go up 1 standard deviation, that would be what, 17.13? Much smaller than that 8, but it's again measuring something different. How spread out are our averages of 50 boards? Well, our averages should be pretty tight. How tight? They have a standard deviation, standard error of 1.13. So what's the probability? Probability that, because it's like we know, still sorry, probability that the mean is longer than 20 inches. Well, 1 standard deviation is it's only at 17. 2 standard deviations up would be what, 18.26. 3 standard deviations up would be 19.39. So it's past 3 standard errors. So this is going to be super, super low by comparison.
Oh,
Does that seem reasonable? And let's put a little bit of like what we might want in this question. Say, there's a big giant pile of all the cutting boards we've ever made, right? And you're gonna get one at random as a here's a present, here's a cutting board, and you're hoping it's a fairly big cutting board, right? Because you want a bigger cutting board. What are your chances of getting one that's 20 inches or more? Well, if you're just getting one, it's a pretty good chance, right? That's your high. Maybe, and I don't know what it is, maybe 40% to 30%-ish, right? You have a pretty good chance of getting a big cutting board if you're only grabbing one, right? Because, yeah, the average is 16, so you might get a smaller one, you might get a bigger one, but there are a lot of bigger individual cutting boards, right? Then what we do is we take that giant pile of cutting boards and we organize them into stacks of 50 cutting boards. So big stacks of cutting boards. Again, they're all different sizes, but big stacks of 50. And you go, I want a stack of 50 that are bigger than 20 inches. Now, okay, I'm not going to be too greedy. I don't want a stack of 50 where they're all bigger than 20 inches, but I want a stack of 50 that are going to average bigger than 20 inches. There aren't very many stacks like that, right? You'd have to have a stack where a significant amount of them were bigger than 20 and very few were smaller than that 16, right? So finding that average of 50, that stack of 50 being bigger than 20, well, that's not only is it low, it's super low. there's just not going to be very many, if any, stacks like that. Does that seem reasonable? But how low is low? Because it's normally distributed, due to the sample size being bigger than 30, we can actually calculate that. That's our norm dis. Michelle, thank you for reminding me it is the CDF. It's the only one we use, so I tend to kind of leave it off. But I should be careful about that, so thank you, Michelle. The normal distribution, we want 20 or above, so 20 to 199, so 20 to infinity, where our mean is 16, and our standard deviation, well, are we looking at the population or are we looking at the sampling distribution?
Sampling.
Then we want to use that standard deviation of the sampling distribution, aka our standard error. So we'll look at that value in a second, but just to reiterate back up to our kind of big picture idea here. In this example, this is a distribution of board lengths. If we took a sample, each of those samples are size 50, but they're size 50 boards. So these are still board lengths. As soon as we put those averages into a sampling distribution, the sampling distribution isn't board lengths anymore, it's average board length.
I think that's where my brain says, I don't know what you're doing. My brain's not comfortable with that yet, I think.
And that's why I'm kind of spending a lot of time not bragging about that, but kind of reiterating that over and over again, because that's the weird thing.
We're looking at.
It does.
Completely.
Yeah.
So what happens if, I forget what happens if it goes below 30? I know I read it, but if you don't have 30?
If you don't have 30 and the original population is normal, you're still safe.
Which would be above 30. The original population was above 30.
The original population is just normally distributed, whatever it's like. If our original population is something that's normal, no matter how big it is or small it is, our sampling distribution is always normal.
Which depends on what we're looking at.
Which depends on what we're looking at. But regardless of what we're looking at, if the sample size is large enough, it's still normal.
Okay.
So yeah, these are individual items. These are individual items. These are stacks of items. These are a big pile of whatever our sample size is. It's average. And that's the important thing about that sampling distribution, is to realize that you've changed what you're looking at.
Right.
Even though this value is the same as this value, even though the board length of 16 is the same as this 16, this is a length. This is a average of 50 board length.
Yeah.
Which I get is weird. Which is why we're spending so much time calculating.
Yeah.
Does that help though? Like you said, yeah, that help? Give it time. That's fair. That's fair. So let's say we have some normally distributed population. So let's say the average student is, let's go with that. The average student has a GPA of, let's say, 2.7.
You're telling us it's an average, or you're telling us it's normal because of the type of problem that it is. But we would normally have to read it and figure out that that would be a normal distribution.
In a question like this one before, it clearly wasn't normal because of that age.
Right, because nothing could be smaller than that. That would mean it wouldn't exist.
Right.
But
It didn't have to be normal because we weren't asked about the population.
Oh,
And our sample size was large enough.
okay.
But in this question, we're going to say the GPA has an average GPA of 2.7. We'll say with a standard deviation of, let's say, 0.3. And I'm going to say and is normally distributed.
Oh, okay.
If your population is going to be normally distributed, you have to be told that.
Okay, okay.
Like this first question said, this population is normally distributed.
Okay.
Fair?
Okay, yeah.
And if the population is normally distributed, we get a lot of freedom from that, because then we can not only ask Chapter 7 questions about our population, we also will get a normal sampling distribution with any sample size. Let's say a class has 25 students. Now, immediately that might make us nervous because 25 is less than 30. So, but in this case, what do we know the shape of our sampling distribution is?
It's normal
How do we know it's normal?
because they told us.
They didn't tell us the sampling distribution was normal. They told us
The population's normal.
the population was normal, which by implication means the sampling distribution is normal no matter what.
Okay.
I know I'm being very picky there, but that's that distinction between which one are we talking about. Fair?
Okay.
They told us the sampling distribution had to be normal because they told us the population was normal. But we have to know that. Fair? Now, if this problem instead hadn't said normally distributed, but this was 40 students, and now somebody asked, what is the shape of your what is the shape of your sampling distribution?
It's still normal because it's above 30.
Because the sample size is large enough.
Right.
Yeah.
But if it was still 25,
So if it wasn't normally distributed, and we said the class had 25 students, and somebody said, what is the shape of the sampling distribution? We don't know. It's probably pretty close to normal, but it might be normal for all we know, but we don't have enough information to say that.
so that means we can't proceed with the problem, correct?
Right.
Okay.
Or we could, in a practical application, you could proceed with the problem. Okay, I'm going to assume it's normal and get an answer, but you'd have to say, okay, this is my answer, but I'm assuming something. You know?
Oh, okay.
Or be careful about it. So in practice, you often don't know, but it's like, this is the best I got.
Okay.
So let's try. Fair?
Okay.
And we'll actually in Chapter 9 have ways to mechanically compensate for that. So because this is normally distributed, the fact that it's only 25 students doesn't bother us. It's still a normally distributed sampling distribution. So you select a random student. What is the likelihood they have a GPA under, oh, let's say 2 point, no, let's just say under 2.
So we would draw our normal distribution bell curve with a mean of 2.7. And our standard deviation is 0.3. Well, really just as 25 students. If you select a random student, what is the likelihood? So 2.7. Enter. 3.6. So what? We're going to be looking for under.
Yep.
Curve. Yep.
So this is going to sound like a weird question, but where does this random student live? So how are we supposed to know that? Central Point, Phoenix? I don't know. This random student lives in the population distribution. That's our individual student. Fair? We're told, as you said, the population distribution has a mean of 2.7 and a standard deviation of 0.3. So if we want to know, what is the likelihood, what is the proportion of these students that have a GPA below a 2, that's just our chapter 7 questions, right? So norm, dis, CDF, we do the nice negative infinity to 2 with a 2.7 and a 0.3 mean and standard deviation, and get something like what, 2%? Or less? I don't know. What is it?
0.0098, so almost 1%.
Oh, 0.009. So almost 1%. Okay. So I'm just going to say about 1%. Now, does that seem reasonable? There aren't very many students who have, in this example, in this class anyway, grade point averages of less than 2. The standard deviation was 0.3, so that's more than 2 standard deviations below the mean, so the chances are pretty low. But still, you got a 1 out of 100 shot. That's not crazy. It's just not very likely. What is the likelihood that a whole class of 25 students has an average GPA less than, do you want to stay with that less than 2 to compare them, or do you want to use a different value? Michelle, you want to stay with the 2? Okay, less than 2.
If we stay with less than 2, it's going to be like super small.
Super, super, super small. And that's a nice thing to see by comparison. But it's also a very nice expectation to have. You know, and you can imagine, you have a class of 25 students and you look around and you go, okay, I bet that student has a GPA less than 2. Just because, you know, you can always see it in their eyes, right? Not true at all, actually, but I'm often very surprised. But, you know, having 1 in there, okay, that's going to happen, right? You walk into a classroom and go, I bet this class averages less than a 2. That's a much more dramatic situation, right? Much less likely. So, what's the difference, though? Or how do we express that difference? Where does this average of 25 students live?
In the sampling error. What?
That was very, very close.
This average, it lies within the sampling error?
Sampling distribution.
Sampling distribution. Right. It's weird when you say it like that. Like my brain doesn't want to connect it. Where does it live? Sampling distribution.
Now, the sampling distribution still has an average of 2.7, because still the average class of 25 students will have an average of the normal average. Average of the average is the average. It is fun to say that, the average of the average is the average, because in that statement, each of those 3 averages are different. The average in the sampling distribution of the averages, each of the averages in the sample distributions, is the average of the population. They're all different averages. It's fun. But notice, even in my drawing, it's much tighter, because instead of a standard deviation of 0.3, we have that standard error. We can use the formal standard error of the sampling distribution, but standard error. And you are familiar, right, in that regard, that it lives in a place that uses standard error. So it's our original 0.3 divided by the square root of 25. We're back to having nice perfect squares. Which is, what, 0.06?
Yeah.
Yes.
Which is much smaller, tremendously smaller, by half an order of magnitude smaller. So that chance of it being out here at 2, notice it's the same 2.7, it's the same 2, But how much of that curve is down here at the 2 now, considering how tight that distribution is? Much, much, much less. That's why Andrew was saying it's going to be really small if we do that. Yes, absolutely it will be.
It's gonna be 0. Is that right?
Yeah, it should be close to 0.
I came up with 0.
That's
Yeah,
what I got too.
Yeah, that just means the calculator can't handle it. The calculator's going, no, dude, no, leave me alone.
Oh, you mean it can't go any lower than that?
Yeah, the calculator's just going, no, I can't. I can't handle how small that number is.
Okay.
So up to 2 and the 2.7 with the 0.06. And the calculator's going, no. I'm surprised. I didn't think that would break the calculator. Near 0. We could bring out Excel and make Excel do it. Excel can be accurate to 127,000 decimal places. It'll give us a number, but it'll be stupid small. And yeah, that's something like 20 standard deviations out. It's not going to happen. Now, here's a fun thing. What if we change that to less than, say, 2.5 instead?
So we got to go back and refine our average,
Refine our,
our probability, I mean, our
Yeah.
population distribution. Yeah.
well, the population is the same, right? Nothing
Right.
changes there. Our standard error is the same. Our standard error is based on our population and the sample size. So looking for that 2.5 doesn't change anything in our standard error. The only thing that's going to change is this value. It's going to change to 2.5.
Oh,
Fair?
oh, okay.
You want to have to do more work than that, though, right?
That's good to know.
Kind of like emotionally, it feels like there should be more to do than that. Nah, it's just one little change. And it should still be pretty small. I mean, 0.6, that's still more than 3, but less than 4 standard errors. So it's still going to be pretty small. What is it with the 2.5?
I got 4.29 to the e to the -4.
So 4 point what? 4.29?
29 e to the -4.
So that's what, 0.04%? So it's still tiny because that's a very tight distribution.
That's cool. So you just have to, you could just change that number to find out all the differences.
Yeah. Somebody goes, well, what would it be at 2.6? Okay, change it to a 2.6. All of those questions happen in the sampling distribution, and we built the sampling distribution. So we can then ask any question we want based on that sampling distribution. Heck, we could even say, I want this probability to be the same 1% as it was before, for sake of argument. Could we figure out what that value has to be to make it 1%? If only we had some sort of inverse normal tool. Inverse norm. And we what, gave it the probability, right? And then the mean and the standard deviation, but because we're asking this question in the sampling distribution, we give it the standard error. What value does that give us back?
2.56.
2.56. Okay, so at 2.56, that gives us the same 1% chance that the whole one randomly selected student under 2. So this, a GPA of 2 is a 1 in 100 bad student. A GPA of 2.56 is a 1 in 100 bad class. By comparison. So yeah, all our distribution tools work. They're just talking about a different object now. Instead of talking about the individual students, they're talking about averages of individual students. Or averages of groups of students, I should say. Even more precisely, averages of a sample of students. Questions about that before I mess with you? My next goal is to throw you off as much as possible. No. Well, sort of. Yeah, we'll see. So let's change this problem a little bit. Let's say the the chance that you will win a game is 45%. You play this game. How many times do you want to play this game? 100. Okay, 100 times. What is the likelihood you will win 50% of those games? Let's say one more. Now, first off, before I give you a couple minutes to think about this, if the chance we will win a game is 45% and we play the game 100 times, what is the expected number of wins we would get? 45% chance we'll win. We play 100 times. How many are we going to win on average?
45.
45, right? So if we play 100 times and want to win 50% of those, we have to be on a good streak, right? So that's less likely than maybe we'd like. What's the chance that we'll win 45% or more? 50-50. What's the chance that we will win 50% or more? Less. So that has to be a good day or a good run. Fair? Is that possible? Sure, it's possible. Our question is, how likely is it? Is it possible to win 100% of them? Yeah. It's probably not going to happen, but it's possible. So, let's look. First of all, what does our population distribution look like? Well, our population distribution looks like a win at 45% and lose at 55%. Why does this population distribution look so different than any of our others so far? Let's say binomial distribution question, right? This is not a distribution of values, of grade point averages, of heights, of lengths, of whatever. This is now a binomial question. This is a yes, no, pass, fail, win, loss, right? So that changes what our population looks like. So if we were to then go take a bunch of samples to look at individual sample distributions, and we're going to say of size 100 in this case, we'd expect those to still be near 45, 55, but you know, some samples of size 100 will be worse and some will be better in terms of our winning percentage. But they should all, you know, be roughly around 45, 55. So we might have here a proportion of, say, 0.43. This might be a proportion of 0.47. This might be a proportion, heck, this could be a proportion of 0.6. That was a, you know, good winning streak. This might be a proportion of 0.38. Fair? Those are all the different possibilities that could happen. In that list of all possibilities, there is the, you know, you lose all 100, P is 0. That's going to happen at least once in infinite amount of time. There's also going to be one that's got the I win all 100 times and lose none, so a P of 1. But most of them, the vast majority of them, are going to be near 0.45. Is that fair? And then if we take all those sample proportions, notice they're sample proportions, not sample means anymore, right? Up here, we took averages and distributed those averages. So sampling distribution of averages. Here we have a bunch of sample proportions, but we're still going to make a distribution of proportions. So this is still a sampling distribution. Just this time, it's of proportions. Now, what's it shaped like? What do you hope it's shaped like? See Camilla saying, normal. Hope it's normal. Well, we expect, again, most of them to be around 0.45. Some a little bit less, some a lot less, some a little more, less a lot more. It's still going to generally be normally distributed. If what? Normal if what?
Is your sample greater than 30?
Unfortunately, no. But it does depend on the sample size. You're absolutely right. The sample size has to be large enough. But the threshold isn't 30 anymore. Now, if you remember back to your chapter 6 quiz, this question came up on your chapter 6 quiz. Like, dude, that was like a week ago. It's normal if n times p times q is greater than 10. Remember that rule? Vaguely, anyway. Somebody told me that once. Yeah, that NPQ's got to be bigger than 10. Essentially, this rule handles very, very small probabilities. If the likelihood of you having a success is, say, like 0.5%, if your sample size is 30, you'd expect to not have any wins whatsoever, right? You would need a much bigger population to have small probabilities ever occur. Fair? So this allows that to account for very, very small probabilities. If the probabilities are, fairly 50-50-ish, a sample size around 30 can still be enough. But the more dramatic those probabilities get, the more sample size you need. So that NPQ, lots of people will say if it's bigger than 5, you're okay. Some people say it's got to be at least 15. The 10 is a fairly middle ground, value. So we want to test that. Is 100 times 0.45 times 0.55, is that bigger than 10?
Yeah.
It should be like, what, 23, 24, something like that.
And 4.75.
24.75. And it's certainly bigger than 10, so yes. Cool. So slightly more complicated threshold, but still that idea, the sample size has to be large enough. It's no longer as simple as more than 30, but still. Now, since this is a nice normally distributed curve, it should have a standard, I'd say standard deviation, but since it would be a standard deviation for a distribution of samples, notice standard deviation of the distribution of proportions, as opposed to a standard deviation of means. This is a standard deviation of proportions. We'll still call it standard error to say it's the standard deviation of a sampling distribution. So it's still a standard error. But if we tried to use that other formula, if you tried to use, it's the population standard deviation divided by the square root of the sample size, I'd complain because we don't have the standard deviation of our population, do we? So what do we need then?
Standard deviation of the proportion.
You either need the standard deviation of a proportion, which we could go find, or we just need a different formula. Remember, I said this formula was the standard error for a distribution of means. This isn't a distribution of means anymore, right? What's it a distribution of? Proportions. So it has a different formula. Square root of PQ over N. If you do happen to remember that the standard deviation of a binomial distribution is the square root of PQN, taking that and dividing by N, it builds itself fairly nicely. But we can just go with this. So I've been trying to warn you about this, right? That sigma divided by the square root of N is specific to a distribution of means. This is a distribution of proportions, so it has a different standard error formula. For those of you who go on in statistics, you'll get to talking about sampling distributions of standard deviations. It's called a chi distribution. It's very important. It has its own standard error formula. If you were doing a sampling distribution of medians for some reason, I don't know why anybody would, but you could, it would have its own formula for standard error. I can't anybody do it. But anything you want to find a distribution of will have its own standard error. These two and the distribution of standard deviation are the three most important. We're only doing these two because the third one's weird. Just gonna go with that. So we only have to know these two, but it's important to know these two. Fair? And again, it's not too hard to find. We know P, we know Q, we know N. So as long as we know to use the right tool, the act of using the tool is usually not that bad. So what do you get for that standard error?
0.0497.
0.0497, you said?
Mm-hmm.
97. Okay. And this is a percentage, by the way, because this 45 is a proportion, right? This 45 is a 45%. This standard error is about 5%. So what is the likelihood that you'll win 50% of your games? Well, 50% of your games is really only about one standard error above the mean. That's not too bad. It's not great, but it's not too bad. So this is a normal distribution. So if we want to do it formally here, norm just CDF. We want to go from 50, well, 0.5 to infinity. With a mean of 0.45 and a standard error, in this case, 0.0497. And that should give us what, somewhere around 15, 17, 16?
Point 1572.
1572.
1215.
So we'll say about 16%. So what is the likelihood that she'll win 50-50? Oh, 16%. So about 1 out of every 6 times you play the game 100 times. 1 out of every 6-ish, sessions of 100, you'll win half or more. That's reasonable. Same basic question as 8.1. This is 8. This, by the way, is 8.2. Same basic questions as 8.1. It's just what we're distributing is proportions instead of averages. And again, for those of you who go on to the second or third stats courses, you'll do this with other descriptive statistics as well, but the process is always the same. The only thing that ever changes is that formula for standard error. And the threshold for it being normal. Cool. So we spent a lot of time in 8.1, and we did that on purpose. Spent a lot of time in 8.1, but the happier you can be in 8.1, the more 8.2 is just recognizing that it's a binomial question instead, so we have to use those tools. Questions about any of that before I let you go, Day? You can imagine these take a lot of practice. I do recommend kind of bouncing back and forth between problems. There's not, unfortunately, the homework assignment for 8.2 is super, super, super short. I wanted to go in and make it longer, but I didn't. And people hate when I do that. But I do recommend go through your 8.1 and 8.2 in your text and look at those problems. And like I said before, just looking through a bunch of them and going, how would I start that problem? What's the key to that problem? Going through and doing a bunch of that to get familiar, as familiar with the language as you can is really helpful. Because as you guys notice, there's a lot of language in here. And this tool is the tool we will use for Chapter 9 and Chapter 10. Chapter 9 and Chapter 10, those problems exist in the sampling distributions of our data. So getting comfortable with this idea is pivotal for 9 and 10. So don't hope it'll go away. Anything I can do for you before I let you go? Okay, if something comes up, let me know. If you guys want to get together tomorrow to ask some questions, I can show up at class time. We missed a day this week. We got through everything I wanted to get through, but these, as I said, take some practice and take some getting used to for the language. So I can pop on at 10:30 tomorrow, and if anybody's around and wants to ask some pointed questions, I'd be happy to answer them. Cool. Okay.
Michelle, are you gonna log back in, or do you have something else?
No, I should probably go pay attention to my kids.
Oh, okay.
But I'm gonna probably work on stuff later tonight, like after 7.
Okay. Okay. Bye.
Bye.
Bye.